So what we want to look at today actually is getting into the final look at Riemann sums in their purest sense. We've been talking about this idea of the Riemann sum using the rectangles. We can use a certain number of rectangles, and we found that if we take the limit as n approaches infinity, then it doesn't matter if we do the left rectangle or right rectangle or the middle rectangles. When you take the limit, they'll all approach the same value. Okay? The Riemann sums, though, can go even further than that, and this is what this example here is meant to show you. Okay? Actual Riemann sums don't even have to have a consistent subinterval. Okay, now the subintervals that we were working with were always delta x is b minus a over n. Okay, and that made all of them the same width. But as you can kind of tell, even if we started with different widths to begin with, if we took the limit as n approached infinity, all of those widths would be approaching 0. Okay? So it doesn't matter if we started out and one was a quarter unit wide and one was 3/8 of a unit wide and the other was 5 units wide. If we were taking the limit as n approached infinity, those would all be shrinking down closer and closer to 0. Okay, and that's essentially the culmination here of the idea of the Riemann sum, is that not only does it not matter if we use left, right, or middle, but it also doesn't even matter if we have them the same width. Okay. Now, one thing I will say is that as you're doing this, what we're going to have here is a difference in our delta x. Okay. So let's read through this and see how this would work. Okay. It says, consider the region bounded by the graph of f of x equals radical x and the x-axis for x between 0 and 1 inclusive. Okay, so you'll notice here we have our function radical x. Okay, there's our radical x. And what we're actually doing here is, rather than having the delta x be the b minus a over n, which would have been a 1 over n, we're actually letting c sub I equal I squared over r squared. Okay? And delta x is the width of the ith subinterval. So notice here, we're actually, if we did b minus a over n, it would be 1 over n. Okay? But because we're dealing with a radical function, I made the widths equal to 1 over n times I squared. Okay, so here I is 1, so it's 1 over n squared is 1 squared over n squared. Okay, then I is 2, so we have 2 squared over n squared. I is 3. We have 3 squared over n squared over n cubed, or n squared. All the way up to n minus 1 squared over n squared, and then n squared over n squared would just be 1. Okay? So those are the different x coordinates that we're dealing with. Okay? And again, the width, in this case, the delta x sub I, we can't just say what delta x is. The delta x sub I is going to be the I over n squared, or I squared over n squared. So what you're going to see as we do this is the c sub I is the right-hand point. Okay? So the c sub I is I squared over r squared, or that should be an n, sorry, typo. Okay, so we're taking the limit as n approaches infinity of the sum from I equals 1 to n. And we're doing f of the c sub I, which is the I squared over n squared. Okay. Now the width of this, okay, the width of this is going to be, well, we can actually derive this a little bit. I didn't finish this completely here. Okay, so that I squared over n squared is the right-hand side of the interval. To get the width, we need to subtract the left-hand side from it. Okay, so we're going to do I squared over n squared minus I minus 1 over n squared. Okay? So if we were simplifying this, okay, whatever I is, okay, we've got an I squared over n squared. We're going to subtract I squared minus 2I plus 1. Okay? So notice we have a 2I minus 1 over n squared. Okay, that's our delta x sub I. Okay? So that's what I need to multiply by up here. So we have 2I minus 1 over n squared. Does that make sense? Everyone with me so far?
Will the width always be 2I minus 1 over n squared when you're...
For this example, okay? So c sub I is I squared over n squared. We were given that. All right?
That's what we were doing.
That's what we're given. Okay? Delta x sub I is the width of the ith subinterval. So we've got to do this by subtracting the two, the c sub I minus c sub I minus 1, you can say. All right? All right, so now we can actually go ahead and figure out what f of I squared over n squared. You might be saying, why in the world did they make c sub I equal I squared over n squared? Well, it's because the function we're dealing with is the radical function. And we wanted to make sure that we would end up getting something that we had formulas for. Okay? So, as we look at this, if I do f of I squared over n squared, that means I have the square root of I squared over n squared. Okay? Now, I know I has to be positive and n has to be positive, so I don't need to mess with a plus or minus here. Okay? This is just going to be I over n. Okay? So, now I'm taking the limit as n approaches infinity of the sum from I equals 1 to n of that I over n times the 2I minus 1 over n squared. Okay? You guys follow how this works?
Yep.
Once I'm here, we're right back to the same stuff we were doing before. Okay? You need to rewrite the sum in terms of things we have formulas for. So I'm going to distribute the I. I'm actually going to factor out a 1 over n cubed. Okay? So we have, it's still the limit as n approaches infinity, but I'm going to factor out the 1 over n cubed outside the sum. And I have the sum of 2I squared minus I. Okay? So, for the sake of writing, I'm going to go ahead and pull this part out. Okay? And I'm going to rewrite that as 2 times the sum from I equals 1 to n of I squared minus the sum of the i's. Alright, so we have 2 times n times n plus 1 times 2n plus 1 over 6 minus n times n plus 1 over 2. Okay? I'm going to go ahead and simplify that further before I put it back into my limit. So let's see, the 2 cancels with that, and that's a 3. So the whole top is going to be a 2n cubed plus 3n squared plus n over 3 minus n squared plus n over 2. Okay? So that is what I'm going to multiply by a 1 over n cubed. Okay? So my final step here is when I have to take the limit as n approaches infinity. What am I taking the limit of? Well, it's this 2n cubed plus 3n squared plus n over now a 3n cubed. Okay? Minus an n squared plus n over a 2n cubed. Okay? So, what's the limit of this first portion? 2/3. What's the limit of the second part?
0.
Yeah, it's 0. Because it's bigger on the bottom. The degree is bigger on the bottom. So this whole thing just equals 2/3. Alright, just to recap here. We got the I over n. We got the I over n by evaluating f for that c sub I. What we're doing right here is we were finding the width of an interval. This is c sub I minus c sub I minus 1. Okay, so you could look at this. Here is where I equals 1, 2, n minus 1, n, alright? So this x coordinate is actually c sub 1, c sub 2, here's c sub n minus 1, here's c sub n. Alright, so to find the width of any one of those, we'd have to do c sub 2 minus 1. C sub 2 minus C sub 1, or C sub 3 minus C sub 2, or C sub n minus C sub n minus 1. Okay? Yeah. Okay, so note at the bottom here, it's a little small up here, but you can see it on your own copy. The reason this particular partition gave the proper area is that as n increases, in other words, as n approaches infinity, the width of the largest subinterval approached 0. Okay? So that's what, that's why this one ended up working. Okay? Alright, so, here's the definition of a Riemann sum, and this will kind of help us, clarify a few things and put it all together. It says, let f be defined on the closed interval from a to b, and let delta be a partition of the interval ab given by a is x sub 0, which is less than x sub 1, which is less than x sub 2, all the way up to x sub n, which is your b. Okay, so those are all the x coordinates that define the partitions, or the rectangles here. Okay? Where delta x sub I is the width of the ith subinterval. Okay? If c sub I is any point on the ith subinterval, then the sum from I equals 1 to n of f of c sub I times delta x sub I is called a Riemann sum for the partition delta. So basically that's just kind of formalizing something there. The one thing I want you to note here though is that notice that we do not require to be f to be non-negative anymore. Before, we were only dealing with functions that were above the x-axis. This allows us also to deal with things that are below the x-axis. Okay? Now it says here, the width of the largest subinterval of a partition delta is the norm of the partition. And it's denoted by this magnitude of delta. Okay, that double vertical line, that stands for magnitude. Okay, remember from vectors, so we had that notation. Magnitude of delta, and delta was our partition. If every subinterval is equal width, the partition is regular, and the norm is b minus a over n. That's what we were using. Okay? So, as the norm of the partition approaches 0, the number of subintervals in a partition approaches infinity. So, as the width of your rectangle approaches 0, this implies that n is approaching infinity. Okay? So again, this is just kind of, I want you to see this kind of in a formal setting, some of the things that we've already worked with here. Okay? This is nothing new, just some new notation and terminology to describe it. Okay? So, here's a new term, and this is definitely something that you need to be very familiar with, and that is the definition of a definite integral. Okay? When we were finding antiderivatives, we were finding indefinite integrals. Okay? Here we're finding the definite integral. It says if f is defined on a closed interval from a to b and the limit exists, as we just described, then what we say is f is integrable. It's a fancy term for just saying we are able to take the integral of it. Okay? Integrable on the interval from a to b, and the limit is denoted by the limit as the norm approaches 0 of the sum from I equals 1 to n of f of c sub I times delta x sub I equals this notation. This is notation we're going to end up using quite a bit from here on out. It's the integral from a to b of f of x dx. Okay, that's how you would read that. It's the integral from a to b of f of x dx. Okay, the number a is the lower limit of integration. The number b is the upper limit of integration. They're the two ends of the interval that we want to work with. Okay? When you are asked to find a definite integral, your answer should be a number. Okay? If you see integral from 3 to 5, your answer should end up being just a number at the end. An indefinite integral, however, is a family of functions. It's that function with the plus c at the end that we were working with before. Okay? One other element here, just to add on here, is that if a function is continuous, then we are able to take the integral of it. Okay? Continuity implies integrability. Right?
Does that mean that the limit as the norm approaches 0, the number of rectangles approaches infinity is just given?
It will exist,
It
yeah.
always exists.
It will exist. The limit will exist if the function is continuous. So that's kind of the nice thing. We don't care if there is a sharp change of direction or something like that. We can handle that. Okay? It's not like the derivative. Okay? If we have to deal with piecewise functions, you just take the integral of the one piece and the integral of the other piece. As long as the junction between those pieces is continuous, it's okay. You can find the integral. Okay? So, this is just some kind of wrap up and formalizing of some of the things, and then revisiting this notation or introducing this notation for the definite integral. Okay. in our practice, we're asked to set up definite integrals that give us the area of the region. Here we have basically this triangle, okay? But if I were to write this as a definite integral, it would be the integral from what to what? 0 to 2, okay? It's what x coordinates. So from 0 to 2 of the function, so of 4 minus 2x, parentheses are optional because this dx tells us where the integral ends, okay? And that's all you need to do at this point, okay? You guys know how to find antiderivatives, but you don't know yet how to handle the area, okay? Now, here's the thing. You can also use geometry to find the values of this integral, okay? This is a triangle. What's the area of that triangle? 1/2 base times height. So yeah, 2 times 4 divided by 2 is 4. Okay, so guess what this definite integral equals? It equals 4, okay? Alright, area of the triangle is 4, so I know the definite integral will equal that. If you have an integral or that you're trying to find, and it's something that's like a geometric shape, like here you have a triangle, here it's just a rectangle, okay? You can use geometry to find the value of those integrals. When there's a curve involved, though, then we're going to have to use the indefinite integral and what we call the fundamental theorem of calculus. Okay, so for things like 16, 17, 18, all of those, we don't know how to work with those yet. Okay? All right.